Hi, let's just move right along. Percent composition, chemical quantities. So I've got a bit of a riddle for you. A little bit of background information. Kosher salt. If you didn't know, kosher salt is usually a little bit different than your table salt in a couple of ways. One, you can see in the image right above my head, kosher salt is on your right. There are sizably coarser and larger crystals than table salt. And then the other one is that table salt is actually a mixture. There's sodium chloride and sodium iodide present. And the reason that is uh, iodine is actually, it is a necessary nutrient, and we don't always get enough of it, so a little bit is slipped in there. Where this one is closer to pure sodium chloride, you can see in ingredients list below, I copied off of Morton kosher salt. Second thing you might need to know about kosher salt is it doesn't have anything to do with being blessed by a rabbi. Kosher salt, I had to research this, is kosher salt in the same way that pickling salt is used for pickling. Kosher salt is used to prepare foods in the kosher way. The coarser salt actually better does what needs to happen. All of this is completely irrelevant to what we're talking about today. I have a problem with the numbers because this is chemical quantities. It says here that your sodium chloride here, its sample is 1.2 grams. And then down here it says 480 milligrams of it is sodium, which would be 0.480 grams if we do our conversion. Well, if I just said that the kosher salt is pure sodium chloride, or close enough to it, right? The yellow prussiate of soda is a very minor component. Last I checked, if this is the chemical composition, shouldn't it be 50% NAs and 50% CLs? Like on the atomic level, we saw that like there's an even number of sodium ions and chloride ions. It has to be neutral. So how is it that it's not percentage-wise what it should be? I mean, this is less, right? 0.6 grams would be 50%, but it's not. So what do we do with that? I want to dig a little bit into your reference tables on right to the side of me. I actually don't know which side. From table T, here's your formula. In chemistry, all composition is measured by mass. Period. The end. Unless, I just said unless. Period. The end. Unless explicitly stated otherwise. If they say percent composition or percent by mass means the same thing, but it's this mass of the part over mass of the whole. So in terms of sodium chloride, for this sample, we have our numbers. We know that the total mass for a serving is 1.2 grams, and that the part being the sodium, we just did the conversion before, is 0.480 grams. We always have to multiply by 100. That 100, by the way, when they say per cent, right, that cent, that root there, that means 100. So you can have per other things as well. And that number comes out to be, when you divide, you get 40%. I mean, that kind of solves it. It doesn't really fully work. I mean, I guess this does make logical sense, right? When you divide out, sodium chloride, this sample is 40%. But I guess, I'm kind of curious if sodium chloride, if it was really pure, right? There's that anti-caking agent. So is that throwing off our numbers? I'm wondering if there's a way we could calculate a percent composition if we didn't have the masses found on our nutritional information. And I think there is. It involves a little bit of an assumption. If we wanted to answer this question here, percent composition by mass of carbon dioxide, like what's it made up of? Well, carbon dioxide's chemical formula is CO2. Well, if we need masses, like we saw in table T, well, what are our masses? Why not just pick a mass? Because the nice thing about CO2 is these chemical formulas are built off of an atomic ratio. And that atomic ratio will be the same whether you have 1 gram or 10 grams or 5 tons. So let's pick a number that makes sense. 1 mole. And I'm picking that mole, I mean, it might sound like it's out of left field on purpose, because we learned before that 1 mole of CO2 contains 1 mole of C and 2 moles of O. And based on our Based on our previous videos, we can then figure out converting those to mass. 1 mole of carbon is 12 grams, and 2 moles of oxygen is 32 grams. Well, now we have our masses and we can do our percent composition. So again, percent carbon is going to be 12 over 44 times 100, which is 27%. And then we do have 2 ways to solve this. If it's only carbon and oxygen, you could say either 32 grams of oxygen over 44 grams of CO2 times 100, and you'll get 73%. Or knowing that carbon dioxide is only carbon and oxygen, you could have subtracted from 100. 100 minus 27 is 73%. So now we know that carbon dioxide by mass is 27% carbon and 73% oxygen. It's not 2/3 and 1/3, but it actually is not too far off, and that's because your masses of carbon and oxygen are similar. I want to show one more example of how this comes out. I'm going to try and shorten it for the sake of brevity here. If we wanted to determine the percent composition by mass of oxygen in each of these compounds, first we need to turn them into chemical formulas. And I know what you might be thinking, right? There's that O4 on potassium perchlorate, but maybe the numbers won't work the way we expect them to only because there's some sodiums in one place and potassiums in the other. The next step would be to set up our conversion between the mass of oxygen in these compounds and the total mass. All of this is going to come from our periodic table. Note that in each case, the mass of oxygen, if you have 2 oxygens in your compound, the mass of oxygen is 2 times 15.999 or 16, so that's 32. For KClO3, that's 48. For KClO4, that is 64. And we are going to the 10th place. It's just that when you have like carbon and oxygen and even things like sodium, the 10th digit is also 0, so I chopped them before. And then all you have to do is calculate your answers. So our initial hypothesis was proven right. Many times it will turn out that, when you have more oxygens, the percent composition by mass of oxygen is higher. But it was good to check because you do see that between sodium chlorite and potassium chlorate, the masses of oxygen, the percentages are a lot closer than you might have expected. So to sum things up, your percent composition formula is there. It's on your reference tables. Please use it. You're using masses, not number of particles. So like SO2 is actually 50% S and not 33% S, since you're going by mass. The masses from the periodic table will do if you don't have any given masses. We're going to go to the 10th place, of course, and you do have to incorporate that number of particles. Make sure you're multiplying and you're distributing as you need to, and the mass of an element in a compound is the product of all of those subscripts. Thanks for watching.